Hello friends, today we'll see how to make load cases for PSC reaction force. So this model we have already been completed. So already we have included the reaction force. Already we applied the reaction forces. Okay, so we will see how to create a load case for this one. So sometimes there may be one PSC working and one PSC standby. Okay, so in those cases we need to make one working and one standby condition. So for those cases, what we need to do? First, we need to check uh, the valve. Where is the isolation valve? In that isolation valve, 1 minute, I will show. Yeah, for example, this is our line. So here, this is your two ball valves are there. Okay, so we'll see this may be your isolation valve. For example, if this PSV is taken for some maintenance, what will happen? There will be a bypass line, or it will be closed here. I think it will, if you close this valve. So what happened? Your fluid will be like this. Fluid will be coming like this up to here. Fluid will be there. So if you close this one, there won't be any fluid up to this portion. Okay. So what happened? Your fluid will be flowing in this direction, and it will be going to outlet, and it will be collected in the pit. Okay. So we will see first how to make such a load cases, how to distribute the temperature for working and standby. This is applicable for the any equipments, okay, any piping. So, or for example, if you have two pumps or three pumps or any vessel, two vessels, three vessels like that. So any working and standby, you have to define the temperature in such a way. We need to check the PNAD, whether it is two working or one standby, or two PSs also working at the same time, or one working or one standby like that. In this case, we'll consider any one PSV. We don't know which PSV will be working, or which PSV will be in standby. We don't know. Okay, or sometimes both PSVs will be working. Okay, so we first we have assumed that both PSVs are working, because already we have made like that. You see, temperature 1, 82 degree, that is design temperature. So both PSVs are working, and temperature 2, this is operating temperature, that is, so both PSVs are working. Go to temperature 3, this is minimum design temperature. In this case also both PSVs are also working. So we have considered that both PSVs are working. Okay, now we are going to consider one PSV will be standby, and one more PSV will be in working condition. So in those cases, what we need to do first, we need to check the isolation valve. Where is the isolation valve? So for this, what we need to do, already we have defined three temperatures: temperature T1, T2, T3. So if you want to make the cases like working and standby, okay. So you need to add the temperature T4, T5, T6, T7, T8, T9, up to 9 temperatures you can add. For example, three pumps are there means, so you can make T4, T5, T6, because three pumps are there. One working, two standby, or two working, one standby, like that you can make. Okay. So in this case, only two PSCs are there. So we are going to use T4 and T5 temperature. Okay. So any case you can select. For this, what we need to do, we need to go to this list inputs, elements. Okay. So first So in general, in working and standby case, what we need to consider, we should not consider the design temperature. Should consider the operating temperature. So in this model, what is your operating temperature? That is T2 is our operating temperature. So what we need to do in this elements here, elements in the elements, your operating temperature is 55. So at T4, we enter 55 at the first node, okay, and in T5 also we enter 55 at the first node, okay. So now if you see the temperature distribution here, we select show temperature, select T4, because now we are given T4 and T5, previously it was not there, okay. So if you remove this one, automatically your T4 and T5 will not be highlighted there, you see, only three temperatures, okay. So like this, if you want to include a temperature T4 and T5, you have to enter like this. Why we are including these two means one working, one PSC working and one PSC standby, like that cases we are going to consider. So now you see if you select T4, so all are 55 degree only. So in this case, what we need to do first, we will see this pump, this PSV. Okay, just close this one and then minimize this. Okay, so first, what we are going to consider, either you can consider this PSV as standby or this PSV as standby. Anyway, that's your wish. Okay, no issue. So I'm going to consider this PSV as standby. So that means you select this one, because from this onwards only, if you close this one, there will not be any fluid. So from this point, you select this one, temperature, double click this double arrow, and from here onwards, there will not be any fluid. So that means you have to consider the ambient temperature. What will be your ambient temperature that you have to consider from your design basis? So already we have defined ambient temperature as 21 degree. So you enter 21 degree at this condition. Okay. So here 55 now need to change. So if you select now T4, you see from here it is 55, but we need this portion only from here to here only. We need 21 degree. Okay, for other these things and all, it should be in operating condition. So first, you need to check the modeling, how we have modeled. So we have gone like this, you see, go to the next node. So your modeling is in this way only. So like this, up to here we have modeled, okay. So up to here we model, after that you need to see where it is going. So it is going in this way. So that means this should be operating at T4. This PSV will be operating. So you need to change the temperature here. You have to select that particular node number, you see, and change the temperature to 55. Now you can see the temperature has been changed to 55. So can you see the difference? So that means this PSV only will be in operating condition, or standby condition. Your fluid is going like this and it is going out, okay, and some portion of the fluid will be stagnated up to here, okay. So in some design basis, what they used to give, your fluid flow will be in this direction. So here there will be some fluid flow. In some clients, what they will ask us to consider means from here, from this portion, from here to here, we need to consider average temperature. But some portion of the fluid will be stagnated at this portion. So they will ask us to consider average. That means 55 plus 21 divided by 2. That means 55 plus 21 divided by 2. So 38 degree we need to consider. Now we will see. First we'll consider only working and standby. That will be in the advanced stage. Okay. So for your basic, so you need to know how to define the temperature for working and standby. So if you're working in some other project, so based on your project requirement, you need to change. Okay. So now T4 is defined. Then go to T5. Select T5 here and see T5 all are 55. Now what we are going to change? So we need to apply up to here. So we are going to consider this PSV as standby and this PSV is working. So again, what we need to do, we know we have modeled like this, correct? No. So our modeling is going like this, and after that it is changing from here. Okay. So go to the valve. We know we are going to close this valve. So where the isolation valve is there, from that isolation valve, you need to change the temperature. Now at T5 from here to 21 degree. So now you see up to here it is 55 degrees. So we need. So what we need to do, your fluid now you see your fluid will be moving in this direction and it should go like this. Okay, so we need to change the temperature from air onwards, from air, because the fluid will be flowing from here. Okay, so you have to consider 55 from here. Now you see it is okay now, because now you see from the PSV is standby for the for this one. Okay, so this PSV is standby now and this PSV is working. Okay, so if you want to apply temperature, you want to change the temperature from here as 38 degrees. So we enter the temperature as 38 degree at T4. That is average temperature, what I told you, for stagnation portion, average temperature T4. Means you can see the difference, 38 degree from here to here. Okay. And for T5, this portion may be stagnant portion. So what we need to consider from here to there, make this known as T5 as 38. So now you see 38 degree. So like this you can consider, but your node number should be perfect. Then only you will get correct results. If you select wrong or node number, or if you apply different temperature, means your results will be wrong. Okay. So now what will happen, we need to see. Because when the fluid flows, then only your PSV will work. So what we need to do, we need to define some more cases. I mean, the PSV reaction force we need to apply, because for T4 this is not working. So we consider 0 here and 0. This vector 1 is F1, force 1. Vector 2 is force 2. Vector 3 is force 3. So we need to update the load case accordingly. Okay. So now F1. In F1, both PSVs are working. So that's why we applied forces in Y direction as well as in X direction. So in vector 3 means that is for temperature T5. So at T5 this PSV is working. So we apply the same force here. Okay, 5715. Okay. Go to this PSV, select here. And in vector 2 this is working. T4. So you make it as 5715 and 5715. And then this case you make it as 0. Okay. Did you understand? No, if you have any doubts, please let me know. So T4. So now what we need to do, we need to define load cases accordingly. So we added T4 and T5. So in the load case editor, we need to update the load cases for T4 and T5 as well as F2 and F3. We didn't add F1 also. So F1 plus F2 plus F1, F2, F3 shall be added to your load cases. Okay. So we will see how to add the load cases. So before that, what we will do, we will define the flange leakage also so that we can see the results together. Okay. So in we'll see, because previously I have done one video particularly for the flange leakage. So in that video, I explained the bolt circle dia in a different way, how to calculate the bolt circle diameter. Okay. So now we'll see, today we'll see how to consider bolt circle dia from the standard. Previously, we have calculated bolt circle diameter based on the formula. That is, general formula is pi by 4 d square, area of a circle. So based on that, we have calculated the bolt area. You see, bolt area is pi by 4 d square. Based on this formula, we have calculated. So now we'll see from ASME B1.1 how to select the bolt circle area. Okay. So first we'll see how many. Okay, so I mean there are different types of flange leakage check. Flange leakage check. Flange leakage check is performed to check. Flange. Why? What is the purpose of flange leakage? Flange leakage may happen due to the forces and moments created inside the piping. Okay, and based on mainly at the gasket area. Okay, because of gasket tightness and also the bolt, because of the bolt, so the leakage may happen near to the gaskets. So in order to check the leakage, so we have different methods. One is equivalent pressure method. This is a general method. So that is ASME Section 3 Division 1 Subsection 3658.1. Okay. So based on this formula, this is a equivalent pressure method formula, 16 MFS divided by pi g square. Okay. So our system design pressure plus P equivalent, this is a P equivalent, plus your system design pressure, your design pressure, line design pressure. So if we add these two values, it should be lesser than that of 1.5 times of rated pressure. So rated pressure will be different. Okay. So we have to calculate based on this. This is equivalent pressure method. So in this, very important parameters to be considered is your pressure, and you have to select the material of the flange, which group your flange material belongs to. Then your gasket load reaction. So this we will I will tell you from where we need to take these values. Okay, and then the second method. If first we need to check with equivalent pressure method always. If any failure happens, then we need to go for this NC3658.3. This is for bolt stress. Based on this formula, bolt stress has been calculated, and it will be compared this results. Okay, EMFS moments, because mainly because of moments. So it is calculating again your bolt circle dia and yield strength of the material, and to calculate the area of the bolt. Okay, so this area only I told you previously, we have done the calculation based on pi by 4 d square. Now we will see based on 1.1 ASME B1.1. Okay, and if this method for some other clients know what they will do, don't use NC3658.3 for stainless steel material. Okay, so in those cases, if any failure happens in ASME, this P equivalent method, then directly you have to go for flange ASME Section 8 division method. That is your detailed method available in CAESAR itself. So that we will see in some other class, because that will be that involves lot of references. So we need to see. Okay. So I will show you some. So this is that ASME Section 8 Division 1 method for the flange leakage. This is a detailed method. So in this lot of reference are there. I will show you the reference. Okay, we'll see some other class. So now we need to see how to apply your flange leakage. So generally flange leakages will be checked at junctions only, means where you are going to bolt from here and here. Okay, so don't consider here. Don't consider here. Okay, you need to consider flange. So you need to check the flange leakage at these two nodes only. For example, in if valve is there, okay, these two nodes we are going to check. But in this case, you see there are no valves, so you have to check your flange at the center where your gasket is attached. No, so that portion only we need to check the flange leakage. Okay. So in this case, there are no other flanges. Maybe one more blind flange is there. Means so at the center point you need to check the flange leakage. Okay. So now we'll see first how to apply the flange leakage for equivalent pressure method. So you select at this node. You can select here also, but I will tell you. Select flange leakage. Flange check is there? No, this flange check. And you see you have to P equivalent method will be there. That is your default method. And here you see from, to, and both they given. From means this node number, because your model is from this direction. Okay, so from is 120. So if you apply, for example, if you select here, from here means, so it will consider your flange leakage at this location. So that is not correct. 2 means okay. So here only we are going to check. Okay, 2 is okay. So instead of this, what I am going to do, if I select both means at both elections, this location and this location also it will check. So instead of defining flange leakage at one location, so we can consider like this. If you go to here, you select both P equivalent, and first we need to check read from file. You see, read from file, and you have to select ASME. Latest one is select, and what is the rating of the flange? Go to this, go to the first one. So your flange is 16 inch, sorry, 16 inch 300 rating, and what is your material? A106 NB. Your flange material is A105. Okay. So here flange is 16 inch 300 rating. Go to 300 rating, and this group you have to select 1.1, 1.2, 1.3 like this. No, you have to select it from 16.5. So open 16.5. So this is 16.5. So select 1 minute. 16.5 is not there. Go to 16. You have to open 16.5. Okay, so this is 16.5. So from 16.5, go to pressure temperature rating. Yeah, you see. So table 1A, it will show the list of material specification. So your material group is this one. So this is your material group. Okay. So this is your material group. So our flange is A105 only. Go to isometric drawings. See, this is A105. ASTM A105. Okay. So this is, you have to select that material. So this is material group is 1.1. So you select 1.1 here and select OK. So you see automatically your flange also got selected. We have selected, and you see temperature and pressure. It will be selected based on the database available in CAESAR. That they took the value from 16.5. So this is pressure temperature rating means in 16.5 you will have the pressure temperature rating. If you go to the next sheet. Yeah. So these are the pressure temperature rating for 1.1 material. So this one already they provided here. So for 300 rating, this value has been tabulated here. Okay, for the particular temperature, what is your value? Okay. And then this gasket diameter automatically it got selected. So this we will take it from be 16.20. Okay, 1 minute. I will. Oh my God. We will take it from 16.20. So 16.20 is the standard for metallic gaskets. So metallic gasket dimension you will find it in 16.5. So here table 114. This is 16 point from 16.20. This standard is 16.20. So what is your size? 16 inch 300 rating. Go to 16 inch. Okay. 300 rating means this is your 300 rating. 16. 16.63 is your ID of the gasket, and 21.24 is the OD of the gasket. So you have to take the mean value, average value. How much? This is in inches. 16, 16.63 plus 21.25. 37.88 divided by 2. 18.94 is it's a main temperature, main diameter of gasket into 25.4. So you will get this value 481.076. Approximately it will be like this. So this has been considered as 442. Okay. So generally it should be taken like this: inside diameter plus the outside diameter divided by 2. We will get the value. Okay. I'll show you some exercise. Oh, sorry. Okay, this is the value. For example, 16 is 16 inch is 1 minute. For 16 inch 300 rating. This is 900 rating. See, for 16 inch 300 rating, what is our gasket? 18 inch. It is 443. What we got it? 1 minute. Maybe I selected wrong one. 16.63. Okay. This is 21.25. Okay. 16.63 plus 21.25. 37.88 divided by 2. 18.94 into 25.4. It is 481 only. For 16 inch, you see 422.4. It is 16.63. 16.63 into 25.4. 422.4. That is correct only. Okay. You see the value is matching 422.4. Okay. And this value is 21.25. 21.25 divided by 2. Sorry, 21.25 into 25.4. 463. Okay. 21.25. Maybe this value may be wrong, I think so. It should be 20.25. 20.25 into 25.4. Ah, you see. But this is also wrong. 514 it is coming. So there are some wrong value given. So like this only we need to calculate. We'll see some other value here. We'll see for 24 inch. Okay. For 24 inch 300 rating, 24.75 and 30.5. So 24.75 into 25.4, 628. ID is matching. Okay, 628.65. Here it is 628.7. Okay, and this one is OD is 30.5. 30.5 into 25.4. So it is 774. So this value is wrong, I think so. So you need to consider average only. So it should be 685.8. So OD of the, oh sorry, this is OD of the centering. Okay. So we need to select here only OD of the gasket. 1 minute. For example, we see 24 inch. Your OD of the gasket is correct, 777. 774, okay. And okay, here they consider 685.8. So 628, you need to select here, you see 628.7 plus 685.8. This is for gasket 24 inch, for 16 inch. This is from Pipe Data Pro. From 16 inch, you see 422.4 plus 463.6. You have to take the average of these two. Okay. So in 16.20, OD is not provided. Maybe we need to refer some other table. We'll see. this one. So now you see, you should not select outside diameter of the center ring. So your outside diameter of the gasket is available here. You need to select outside diameter of the gasket and also inside from here. So you see, as per this calculation, G value can be calculated based on this OD and ID. So our ID is 16.63 into 25.4. You'll get 422.4. That is correct. And OD is 18.25. 18.25 into, sorry, 18.25 into 25.4 equal to 463.6. Okay. So you can select directly or you can multiply. Sorry, you can add and divide 18.25 plus 16.63 divided by 2. Say 17.44 into 25.4. You'll get 442.976. So that is 442.976. This value you got it. Okay. So like this, you need to check the gasket diameter for all sizes. Then go to this next flange. So once you define the flange leakage, so if you select for the other flanges, so it will automatically get repeated. So no need to define once again, unless otherwise there is a change in the sizes and all sizes and rating. Okay. So this we have selected. Only thing you have to select from and to or both. Okay. So now we have defined for this location. Okay. So we'll see for this one next branch. We will select flange leakage from and to. Here the line size has been changed. Line size is 18. So you select read from file 2.9 and it is 300 rating and it is the same material only. That's why I'm selecting 1.1. If it is stainless steel, then you have to select appropriate material of stainless steel. For example, your stainless steel material A182, F316 or F316, yeah. Then you have to select 2.2. Group code is, material group is 2.2. So you have to select accordingly, you see. If it is A182 grade F11, grade F11 means you have to select 1.9. This is for alloy steel. Okay. So you select, here I am selecting 1.1, it is a carbon steel only, 1.1. You see the gasket load reaction now 248.539. If you go to this one for 18s, 150 rating and 16.20. 18s, go to 18s. Okay, so it is 10.38 plus 9.19 divided by 2, 9.785 inches. We are going to convert it to mm, 248.539. You see, 248.539. So that is okay. Then go to this node and select flange leakage. So here we need to check the flange leakage at the center. So you have to define 2 because we have our modeling is like this. So we have model like this from here and it is continuing and it is going. Okay. So you have to select 2 here and here also. The same has to be repeated. Flange 2. Okay, now let's see up to here. You have to model properly. Just I will show in how to select flange leakage check AC is, as per NC 3658.3. Select flange check and NC 3658.3. Okay. So what we need to do first, we need to select bolt circle diameter. So bolt circle diameter you can get it from Pipe Data Pro itself. I'll go to 16.5, you will get the details. Okay. So here first we need to check the bolt circle diameter from 16.5 or Pipe Data Pro. So go to flanges 16.5 and 16 inch 300 rating. What is the size here? 8 inch. So it is 8 inch. So 8 inch 300 rating. Select 8 inch 300 rating. So your bolt circle diameter is this one, 330.2. Or you can select it from this one, 16.5. So this is 8 inch bolts diameter of bolt circle. So 8 inch, this is 330.2. Here it is there, no, 330.2. So enter the value of 330.2. And then bolt area. How to calculate the bolt area? I told you, no, this is from ASME B1.1. To open B1.1. So you know what is the size of your stud bolt, your bolt size. For 8 inch, 7 by 8 inch is your bolt size, or M24. Okay. And the number of holes is 12. So now, I have some Excel sheet. So this is for 8 inch, no? So 8 inch 300 rating. For example, go to here. This is as per 1.1. 8 inch 300 rating. So 8 inch 300 rating bolt circle dia is 330.2 and diameter of the bolt 7 by 8 inch. So here previously I calculated based on pi by 4 d square. Now I am going to get direct value from that bolt area from B1.1. Okay, this is B1.1. So our size is 7 by 8 inch. Okay, and you have to select area from tensile stress. This is your value, 0.462 inch square. This is inch square. So you have to convert that 0.6 into, convert the value into mm square, 0.462. 0.462. So we'll get 298.063. So here 298.062. And number of holes is 12. So you see 12 holes. So number of holes is 12. Then you will get the area, total area equal to 3576.74. So enter that value 3576.74. Okay. So like this you can calculate for all other sizes. So you have to refer B1.1. You have to remember ASME B1.1, table 6. Go to table 6, you will get this tensile stress area in inches square. You need to convert. Okay. Based on your size, bolt size. Okay. And then next is yield strength. So yield strength you can take the value from CAESAR. If you select here allowable stress, you will get the yield strength value 241.311, and this is for the So this is for cold allowable stress. Sorry, that is for the ambient temperature. So generally yield strength will be defined for SYC means for cold, that is for ambient temperature, that is for 21 degree. And SY1 for your temperature 1. Temperature 1 means this is this is design temperature. So SY2 for operating temperature, SY3 for minimum design temperature. Like that you have to define. Okay, so I have to check the values, take the value from ASME Section 2 Part D or ASME 31.3. So I will now we will see how to take the value from ASME Section 2 Part D. So here what is our you see this is a yield strength value table Y1. Okay, this is ASME BPVC, that is boiler pressure vessel code section 2 part D. So you can get the value based on the temperatures. So without temperatures also values are there. You see minimum yield strength, that is for without temperature, minimum value is this one. Okay. So here minus 22 100 degree Fahrenheit. First we need to select the material. What is your material? First we need to see. So material you have to select from here. For example, your material is A182 F316L, then you have to select line number 15. But here in this case we have material of what is our material? A105. So you go to the previous page, you have to select A105. Or you can type also, you will get the value. SA105. This is for the maximum allowable stress value. Our line number is 5. One minute. We will go to yield strength, stress intensity. You have to go to correct. This is your yield strength. Okay. This is your yield strength, and our number is 27. SA105. So go to 27. 27 is our material. So this line number is 27. Why we are selecting 27 means our material is SA105. So we'll go to 27. These are your values. So now we need to see what is our value. So cold is Fahrenheit to Celsius. So our temperature is 21 degree. That is 69.8 Fahrenheit, 70 degree Fahrenheit. So up to 100 degree Fahrenheit, your yield strength is 36. The unit is in KSI. You see, it is given as KSI and temperature in Fahrenheit. So you need to convert KSI to what is our value here? It is in kilopascal. So KSI to kilopascal. KSI to kilopascal. Change KSI to kilopascal. What is our value? 36. 36. 248,211 kilopascal will be your SYC. Let's see, 258. What's the value? 248,211. So we enter that value. 248,211 will be your yield strength for the ambient temperature. And for 82 degree, we need to see what is 82 degree. So 82 degree. So Fahrenheit is 180. So 180 degree means it is coming in between 150 and 200. So in between it is coming. So you can correlate the value or just take the main value 38.8 divided by 33.8 plus 33, you'll get 66.8 divided by 2. 33.4 will be KSI will be your SY value, yield strength value for 82 degree. 33.4, enter 33.4, you will get 230.284. Here 230.284, to enter 230.284.9. You see your temperature increases, yield strength value gets decreased. Okay, so like this you need to check for 55 degree. 55 degree, that means 55, 131 will be 131 Fahrenheit. So 131 means it is coming here. I will get main value between these two. Main value of these two. Ours is 27, 36 and 33.8. 36 plus 33.8 divided by 2, 34.9. So 34.9 KSI, 34.9. So your yield strength value is 246 to 7. 246 to 7. Okay, like this you need to enter all the values. So this is comes under 5 degree. That means it is within 100 degree Fahrenheit only. So you can take the value from here, or you enter all the values like this. You have to select correct, you have to enter correct yield strength value based on the temperature. Okay, so T4 and T5 is this value. So we can select T4, T5, this one. So like this you have to do the analysis. Sorry, flange leakage values you need to enter. Go to the next flange. Here you have to select both, and here we need to select both options, because previously we have selected I think 2 options. That's why it is coming like that. So previously used 2 options. So here you have to select both. Then only your flange will be checked at this location. Okay. And then once you completed, start run to check the errors. And you see some error is coming 122, 140. Yes. Why it is coming? We have defined, we have selected flange leakage, but we have not entered the value. You better double click and delete this one. Now you select start run. Okay, you see some of the errors are coming. This bend is long enough, not long enough. That means I told you previously some error will come. What is the value? Total value 121.337. So what is a 45 degree value for this you consider as 45 degree elbow. Go to fittings, but welded fittings, 45 degree elbow, and what is our line size? 8 inch. So it should be 127, but we are given as 121. So it should be 120. If you enter 127, sorry, not 1127, 127. And what are all the other errors? You see 3390, 3410. Here also bend is not enough, means in the vertical. Here we have lengthy line for 8 inch. 90 degree, what will be your bend dimension? This is 90 degree, and for 3 inch 114 will be your dimension, but here 113 is there. You have to enter 114.3. Okay, and go to the next error, 4030. Yeah, this one I told previously. If you are given exact flange, elbow dimensions, then you have to double click this, or you have to delete this. You should have only the midpoint, because for all elbows, minimum 3 nodes should be there. Go to the next node, you see. You select this one, on the error you go. So again the same error only. If you go to vertical, you have to change it to 114.3. Then here 5030, bend angle specified for the bend element 502 within 3.63 degree. Bend point, either use bend forend or point. That means so you see we have specified bend. We have specified bend at this location, but there will not be any bend, no? Just straight pipe only. So you have to delete this bend one. So now if it's, I think all errors we have highlight, yeah. We have focused on all the errors. Now if you run this one, start run, you see there will not be any errors. Okay. So what we need to do, go to this load case editor, start run. Load case editor. We will see how to define the load cases for T4, T5, that is working at standby. So it is already been defined here, you see T4 and T5, edit at T4 and T5 like this. Okay, already this load cases has been updated. So this is a recommended load cases. Add a load case means you have to add, or you can recommend it. CAESAR recommended load case. I think this is a CAESAR recommended load case. Accept means it will come like that. Okay. And if you want to import the load cases, here option is there, import load cases, or you can import from Excel files. If you have any Excel file, then you can import from the Excel file load cases also. See, if you have any such load cases, so you can select, for example, if anything is there. Yeah, this is error, maybe that is not a load case one. Or you go to any CAESAR model, for example, go to this CAESAR model, you select this one, okay. Open. You see the load case has been changed because we have imported a load case from other CAESAR file, okay. Close this one, I will tell you. So since this is a buried model, sorry, this involves buried model. So what we need to do, close this, and you have to convert this into buried first, underground modeler. Okay, then already I think we have defined the buried portions. In the last video, if you check, you can see we have already defined this two model, and you convert this one. So if you have buried portions, then you have to convert above ground model into buried model. Then only you have to add the load cases. Go to static analysis. Here, static analysis is so go to piping input. And then start run. Here again you need to check. So there are no errors. So now you can see edit static load cases. So if you have any buried model, in the buried model only you need to change the load cases. Okay. So T1, T2, T3, T4, T5. Okay. So already we have seen how to add U1, U2, U3 and Win1, Win2, Win3. Now we will see how to add. Already T4 and T5 has been defined. So no need to add anything. This T4 is for T4 and T5 is for working and standby. So now we are going to add here. So what we need to do, we need to add operating temperature or design temperature. Copy this plus F1. This is for PSV reaction force. Okay. So now we will change this one as operating temperature. Then you need to add two more temperatures. Okay, that is for F2 and F3. F2 is for on PSV working, on PSV standby. So that is for T4 and T5. So what we need to do, we need to copy this T4. Okay, plus F2 and T5 plus F3. Okay, so you have to select OPE here. And here also OPE. So like this, we have added these three cases, and then go to the next node. Like what we did do for wind and seismic, the same like that we need to consider. We need to consider occasional cases also. For occasional cases, then how to array the occasional cases means W plus T1 plus P1 minus of W plus T1 plus P1. So W plus T1 plus P1 will get cancelled, you will get only F1. That means L13 minus L2. L13 minus L2. So here you need to define L13 minus L2. This is occasional cases, OCC, because only reaction force will be there. So safety valve reaction force is an occasional case. Every time will not occur. Okay, once your design pressure exceeds, then only this reaction will occur. And then next is, since we have used T4, so you have to subtract with respect to T4. L14 minus L8. L14 minus L8. And this is also occasional. Then next is L15 minus L8. Because T5 we use, so T5 where it is available, L10. So L15 minus L10. Here also occasional case. So if we have wind and seismic, so after defining wind and seismic, then you define the safety valve reaction force or slug force or surge force. So anything you define like this, uniform loads, then wind load, and then concentrated forces like PSV or slug or surge. Okay. So for AC purpose, I have deleted other load cases. I have added this one. Okay. So go to again, you add 3 more cases. Okay. So now this is only F1 and F2, F3. Now we are going to add this with sustained case. That means L11. Sorry, L12. L12 is your pure sustained case. L11 is alternate sustained case for temperature 5. So L12 plus L16. That will be your W plus P1 plus F1. So you have to select occasional and you have to select scalar. Okay. So there are many things. You see, algebraic, SRSS, absolute max min. That and all I will tell you later in different load case combination. Okay. And then next is L12 plus L14. Sorry, L17. L17 is nothing but F2. You have to again define here. Sorry, L17. Occasional, and you have to change this one to scalar. Then L12 plus L18. That is your F3. Occasional, and then scalar. So like this you have to define forces for reaction forces or slug force or surge force. Then you say this one. It will show because already we have defined wind and seismic, no? So I have not used anywhere. Just you continue and run the system. Continue. Then do the analysis. Yeah, some failure is there, we'll see. So we need to check. So if you want to change anything, you have to go to the above ground model. Then only you can change. You see, go to above ground model. This is above ground model, which includes B means buried model. Go to the above ground model. So in the now I need to check the load cases. I will show you for flange leakage how to apply. So you see now this load case has not been changed because in buried portion only we have changed. So always build the load cases in the above ground model. So I am going to, you see, import load case. I am going to import load case from the buried portion. So this .j is your load case file. Now I am selecting this. You see, it got selected from the load case file from the buried model. Okay. So I forgot to tell you one thing regarding flange leakage. So you see, if you are not selected anything here, this flange analysis temperature, your output result will not appear. I will show you. Okay. So now I saved this. Continue and close this. And I'm going to the buried model. Because buried model only we need to check the output. I see there are some failures on the occasional cases. We'll see. First, if you check the temperature in P equivalent, pressure of flange P equivalent, select any one load case. Check the P equivalent. You see, there is no result. You see, all are showing 0. That means you are not selected properly the temperature. So you have to select the temperature, then only you will get the result. Otherwise, you will not get the result. Okay. So go to the above ground model. The static load case, edit static load case. And then here you select the flange. For hydro test case, you select T ambient. So ambient temperature will be there. And for T1, you select T1 and don't consider alt sustained. And T2 means T2, T3 means T3, T4 means T4, and T5 means T5. And then for sustain, this is sustain, T ambient you select. And for this case, you select T1, T4, and T5. Okay, you save this, continue, give continue. Okay. So close this, convert this one into buried. Select OK. Okay. And open piping input. Now in the buried model, we'll see whether the load case has been updated or not. Here, go to here, edit static load cases. You see the temperature has been updated. Okay, then you run this is analyze. Now we will see hydro T1, T2, T3, T4, T5, sustain, and again other 4 cases. Check the flange P equivalent. Already we have defined something here. This is customized report. If you want to report as a summary, for example, select P equivalent 1, 2, 3 like that. So what happened means it will comes in a different window. You see 1, 2, 3 like this it is coming. Okay. So instead of this, we can customize the report. I will tell you how to customize report in later. So instead of this, if you select all this one, it will come as a summary, like a summary. You see, all cases in one in one file itself. So at node number 140 P equivalent, it is failing 110%. Okay, all P equivalent it got failed. So that means if it is failing in P equivalent, then go for NC method. It will get passed. Okay. So or if it is a stainless steel, then go for section 8 division 1 method. Okay. It is in NC method, all the flanges whatever we define it is getting passed. Okay. Like that only you need to check. And regarding this occasional cases, maybe it is failing, we will see why it is getting failed. So I will tell you how to check the outputs and all, what are all the things to be checked. We'll see in the next class. Thank you very much.